Let's look at the case where we mix together an s orbital and two p orbitals. And of course, we're going to be mixing whatever our valence level are. So we don't have the choice of every electron on the atom. We're only going to be working with the outermost. So we're going to have our outermost level, one of those. We're going to have our outermost n level with two of these. So two of the p orbitals, one s orbital. Notice that gives us 1, 2, 3 orbitals total. We're going to mix together 3 orbitals on this central atom. And of course, we'd have to work through each of the individual atoms on a bigger molecule. So we've got a total of 3 orbitals. That means we're going to mix 3 orbitals in the blender, pour them back out. We should get a total of 3 of these Sp2 hybrids. Now, if we were to do that, this is going to end up telling us that we have 3 regions of space with electrons, which is the exact same thing that the notation AX3 was telling us back in the VSEPR notation. So, if you want a quick shortcut to get between them, I'll remind you that we can just look at the number here, we can look at the total number here, and those two will match up to have the same geometries. So, if we have Sp2 hybrids, it will be the same family as AX3. If we had the Sp3 hybrid, it'd be the AX4 because we have an S and 3 Ps. So you can just add up those two numbers and just interchange between the two theories very rapidly. So there's a lot less memorization than this chapter may have made you think in the first place. So let's use boron as a test case. Boron's going to have 3 valence electrons. It'd be helpful to have a quick sketch of our periodic table up here. This is the sort of thing we should be able to do. That's why I haven't put an actual periodic table image here. I want us to be able to just sketch it and quickly picture where something's at. So remember, we said boron and beryllium. We said these ones are allowed to make electron-deficient molecules before. We're finally going to talk about the energetics that are involved. Remember, we didn't bring up energies much when we talked about VSEPR. But here, in our valence bond theory, we actually are going to consider our energies a lot more. So, let's see exactly why these worked out. Because remember, we had to get very hand-wavy when we talked about beryllium earlier. We had to say that, about boron, it was allowed to get away with looking like a 2s orbital. Somehow magically, even though it does have a p electron. We said, well, yeah, but it's like it's totally a full valence shell because this looks so much like helium. But this doesn't look like helium at all anymore. We have an extra electron on it. Well, we're finally going to put that issue to rest by talking about the Sp2 hybrid orbital. Now let's look at the energy sketch of it. And you can ignore the gray area and you can ignore the dotted lines for the moment. And also ignore this section. We went ahead and we filled up our 1s electrons, we filled up our 2s electrons, and then we had an extra electron that still went up here into the 2p orbitals. Just like we'd expect from the periodic table, we fill up our 1s, we fill up our 2s, we end up with one more electron and it goes into our 2p's. Okay, now notice that if we have 2 low energies and 1 high energy, and we end up averaging those energies, we're going to have 2/3 of the energy between them for all of them. And that's exactly what we see over here. This will be 2/3 of the way between those energies. The average energy is still the same. So we aren't getting any free energy, but we're not costing any energy either in order to mix them like this. But here's the thing. We no longer have to have these 2 electrons sticking around in the same region of space. Now they're all going to have their own declared regions of space, and they're not going to interact as much. That's a good thing. That means that this will be more stable, even if the energetics are the same. Now what about that p orbital that we didn't mix? Remember, that was still hanging around. We only took 1 s orbital and 2 p orbitals in order to mix them. Well, we end up having that p orbital still, but who cares, because right now it's empty. Well, I'll tell you who cares in a minute when we actually get to the shape of this in 3 dimensions and what this actually implies about how things are being shared. Okay, so we've got this empty region of space that could allow electrons. In this case, it isn't. We have 3 regions of space with electrons. They're all going to be spaced out evenly, and we know that AX3 family of geometries is going to be trigonal planar. We're going to have a bond there, there, and there, with a central atom here, and then whatever's going to be happening will be sitting at the end of each of those bonds, or if it isn't a bond, it could just be an electron cloud, so a single orbital. Either way. Now that 2p orbital, this would be sitting there coming in and out of the paper, but it's totally empty. There's no electrons in it right now. That's the shape that we're talking about. Now suppose we bring in, oops, let me get rid of that ink for a second here. Now let's say that we have fluorine atoms coming in. Each of those fluorine atoms had 7 electrons because these are halogens. We're going to have one orbital that's still empty. So it's going to have only 1 electron for the fluorine to start with. This other electron was originally owned by the boron. We bring them close enough together that they overlap. We now have a bond. The bond contains 2 electrons just like we expected. We're saying that it's spending its time right here between these 2 atoms. That's going to be the case for each of these as well. So we see that we're going to end up with that trigonal planar geometry just like we expected. We're going to have that empty 2p orbital sticking up and down. And so we can finally see some of the reasons that if we are given BF3, we'd say, okay, we go ahead, we draw a Lewis structure for this. We see that everything's going to be at its octet for the fluorines. Boron is not at its octet. We say, oh, that's weird. We look at the periodic table, are reminded it can be electron deficient. We say, okay, it's weird, but it's allowed. And we moved on. Now we can go one step further and say, because we've drawn it in 3 dimensions, and we are aware of the fact that this orbital will stay unfilled, and so all of these end up being kind of like some sort of a new valence level, and they all end up totally filled once they pair up with the fluorines, this should be a really stable geometry, because this higher energy 2p orbital is just staying empty, and it's not interfering with anything, and it's not needed to house any electrons. So we do expect BF3 to be pretty stable as a result. Now that said, you might say to yourself, okay, cool, but how can I think through all of that logic on a test and know that I haven't just made something up that isn't true? How do I know that I didn't forget something important? Well, just remember, our early easy ways of doing this are still true. We're just adding in more detail for why we were allowed to do that counting in the first place. So we can still do exactly what I just described with our Lewis structure. Get to the point where we say, oh, the question says that this is a stable molecule. Wonderful. I will just fill it in the most appropriate way that I can for all of its electrons. That's the logic you need, as long as you understand that this is the reason sitting behind the curtain for it.